We talked about floating point numbers, and here's a little classic example where we have a floating point number that starts out at 0, then for 10 times I add 0.1, and then print it out. So if you add 1/10 10 times, what do you expect to print out? You expect to print out 1, and if we run it, so compile it, run it, and in fact it prints out 1, just like you would expect. But let me change the program a little bit here. I'm going to say if f is equal to 1, then print 1, otherwise we won't print 1. And when I try compiling this program and running it again, we see 1.0 print out, but we don't see 1. And that's because the value written to f is actually not 1. If we ask printf to show us more digits, so by putting .20 there, I ask it to show me 20 digits in the fraction part, then we see that actually it's something that's not quite 1.0. And even then, this is an approximation. So the problem here is that 0.1 has to be represented as a floating point number, which is based on powers of 2, and 0.1 can't be expressed as a finite representation of binary digits. It has to be approximated. And so we add 10 of those approximations, we still end up with an approximation of 1, even though 1 itself can be represented. So beware when you're printing things out that there are approximations different from what you're used to. You're used to decimal approximations, there's binary approximations under floating point. And if you ever need to count up by fractional amounts, usually you need to do something like less than or equal to, or something more complicated to find out when you get close enough. Here's another, here's a different example. We're going back to integers, but talking again about what the standard specifies. There's a header called limits.h, which gives you names like int max. So this is the biggest number you can express as a signed integer. So if I add 1 to that, then since we started with the biggest one and we add 1 to it, what happens? It can't be an integer that's bigger than int max because int max is the largest. So somehow this should fail. And then I've written the same thing except I put it in check grow, which takes an integer, checks whether x plus 1 is greater than x, and returns. So we expect to see 0 and 0 in both of these cases. So let's try this out. And we got a warning, but also 0 and 0 printed out. So what does the warning say? It says that you definitely have an overflow. The compiler can tell that we started with the largest number that fits in an integer and we added 1 to it. And so that's not just a problem with what we might be trying to do, count up consecutively, but it's actually not a well-defined C. And if we use -02 here, that gives the compiler license to optimize the code, to improve the code, make it faster, we often use something like -02. Now when I run it, the answer is 0 and 1. So this warning was telling us something significant, sadly, if I comment out this direct call and only have the other call, we don't get a warning, and we still get 1 where we expected 0. So the warning was telling us something useful, but when you need it more often, like you didn't actually write int max plus 1, you're likely not to get a warning on that, even if I use -w all, which I should have been using. So what's the problem here? The problem is that the C standard doesn't specify what happens with signed integer overflow. It does for unsigned, but not for signed. And since it says that you should just not write C programs that overflow, the compiler is allowed to assume that x plus 1 doesn't overflow, and that therefore x plus 1 will always be bigger than x, and so it just replaces this with a 1 when it's optimizing, when it's trying to make the code run faster. And again, the compiler is completely allowed to do that based on the C standard. It's just unfortunate that it's hard for programmers to tell when they're staying within the C standard or not, but that's what we're working with here in this class. Here's another example along those lines, but this time I'm using unsigned integers. So I'll just use this version of the code. And we'll compile it first without optimizations, but with all warnings on. You notice we did not get a warning. and we got 0 and 0. We didn't get a warning because we're using uint max, that's unsigned integer max, that's the biggest number. And while this does overflow when we add 1, it's a well-defined overflow. It overflows back to 0. Even if we use optimization, O2, then we will get the same answer. Okay. So this is why you will sometimes see C programs that cast unsigned or assigned integers into unsigned, do some arithmetic, and then cast back to assign. Because when you're in the unsigned world here, you don't get mathematical addition, which always, 2 positive numbers always add up to a bigger positive number, but you do get a well-defined modulo 2 to the whatever your word size is, kind of arithmetic. Here's one other thing that I alluded to in previous slides about what is allowed and disallowed. So here I have a function called set, which takes 3 pointers, I, f, and j. I and j point to integers, and f is to a floating point. I'm going to start out by printing the address of f and the address of j. The address that f provides, that is. Not the address of f itself, but the pointer value f. Set j to 1, set f to 0, and then set I to whatever j was. And the punchline here is, what if j and f are actually the same address? Then it would seem that I'm setting j, but then I'm setting f, so I'm setting floating point 0 as the same as integer 0. It's all zeros, so I would expect I to end up with 0 at the end. Okay, so when I call the function, I am setting up that scenario. J is the address of the variable j, and I'm also casting it to a floating pointer, but still the same, and then printing out the 2 results. So what we expect to see is that I is 0 and j are 0 at the end here. Try that out. Without optimization, run the program, and that's what we see. Whether we look at I or j, because the value of j was set to 0 and then copied into I, we see that f and j were both the same address, and that's why we get that answer. On the other hand, I think you knew this was coming, I run it in optimization, and now we get a 1 and a 0. How can that be? Right? If I is 1, the way I got a value was by setting to the content of j, so j must be 1, you would think. But the thing that the compiler is allowed to assume here is that a pointer to a float and a pointer to an integer are different things. Right? It's allowed to assume that if I write to an int and I write to a float, that I'm not writing to the same address. And if they're different addresses, then the compiler is free to reorder them. And if it reorders these two, then it turns out I was just set to 1, so it already knows there's a 1 there. And so it doesn't bother looking in j to get I, it just sets I to be 1. So that's the constraint there. The result again depends on the optimization level. This is called strict aliasing. Aliasing refers to f and j being aliases for the same address. Strict aliasing means that the compiler can assume that they're not. Right? The rules here are a little subtle, but again, the way to work around that to avoid those problems is to use memset or memcopy.